Hi everyone, welcome to our final video for this week. Today I'll be covering how we evaluate and investigate interlayer bond strength along with hardened states characterization. As a reminder, 3D printed concrete specimens are subjected to standard testing methods like those used for conventionally caused concrete. However, they have orthotropic mechanical behavior, meaning their properties vary depending on the loading directions. Several mechanical characterizations testing methods are available for assessing 3D printed concrete material, like compressive strength test. So this measures the maximum load carrying capacity under axial compression and is one of the most common tests for concrete. The second is flexural strength. Either will be 3-point or 4-point bending. This actually determines the material's behavior under bending loads. In three-point bending, a single central loading roller is used, while 4-point bending employs two central rollers to distribute the stress more uniformly. The third test is a direct tensile test. This evaluates the tensile strength of the interlayer bond by applying tension at both ends of the specimen. The fourth one is a shear test. Include various methods like the isopiece test to evaluate shear properties, adhesion, and the fracture energy of the interlayer region. The fifth one is a splitting test. This actually measures tensile strength of the cylindrical or prismatic specimens under diametrical loading. This test helps assess the different mechanical properties such as interlayer bond strength, tensile strength, compressive strength, flexural strength, shear strength, fracture toughness, and others. That actually offering a comprehensive understanding of the material's behavior and the performance. These tests can be performed in different directions, such as orthogonal, longitudinal, plane-side directions to characterize the material thoroughly. We can now discuss about various methods to assess interlayer bond strength before delving into other techniques for characterizing the hardened state. The direct tensile test setups used to determine the interlayer bond strength in 3D printed concrete. That involves applying uniaxial tensile pull-off loads at both ends. It's important to note that there isn't a standardized procedure for this test, leading to variation in test setups. Typically, only 2 printed filaments are considered for this test, although some studies have used multiple filaments. Rectangular specimens are commonly used for direct tensile tests, with circular shapes used to a lesser extent. Steel or metal plates are affixed to the top and bottom filaments, and once fully hardened, the specimens are subjected to direct tension. Tests are often conducted at displacement-controlled rate of 0.2 to 3 mm per minute, depending on the gauge length, or a force-controlled rate of 28 to 50 Newton per second. Some groups utilize notching to ensure failure occurred within the interlayer region rather than within the intralayer. The primary goal of direct tensile test is to induce uniform tensile stress in the failing interlayer region to determine its true tensile strength. This value provides insight into the fusion degree in comparison to caused specimen or intralayer, and serves as a parameter for finite element modeling of 3D printed structures. However, efforts should be made to avoid soil cutting during sample preparation, as it can impact the microstructure of the weaker interlayer region. So preparing sample in the later stages of plastic concrete is rather actually recommended. When soil cutting is necessary, inspecting specimens for visible cracks before the testing is advisable. Notably, tests with only 2 filament layer may experience significant plastic shrinkage due to their larger exposed surface area to volume ratio, making early crack inspection essential, so even without soil cutting. Additionally, sharp notches can lead to stress concentration, disrupting uniform tensile stress distribution in the interlayer region, introducing errors in peak tensile stress determination. Currently, no standard protocols exist for direct tensile tests of 3D printed concrete or similar cement-based materials, although guidelines have been proposed. There's a consensus that rotationally fixed connections should be used at both ends of the specimen to best replicate in situ constraints and post-cracking rotation. However, if ensuring parallel edge connection or gripping in the materials testing machines, or MTM, isn't feasible, allowing one end to be rotationally free is preferred to avoid initial strain gradients due to misalignments in the MTM. To accurately record the full load deformation response, including peak resistance and fracture energy control post-peak softening, measuring deformation across the failure plane is essential. And the displacement control test should be guided accordingly, often using a clip gauge extensometer. Literature often employs a 3 or 4-point bending test as a practical method to assess the interlayer bond strength of 3D printed concrete specimens. Despite the challenges of objectively determining tensile stress due to stress gradients along the specimen's height, lateral tests are favored over direct tensile tests due to their simpler execution. However, in quasi-brittle materials like 3D printed concrete, assuming linear strain and stress distribution can lead to overestimation of the actual tensile strength. In bending tests, the vertical orientation is crucial to induce tensile normal stress in the interlayer regions. 4-point bending is preferred for interlayer bonding strength characterization as it ensures similar tensile stress on more interlayer regions, allowing the weakest one between the central rollers to govern failure. On the other hand, 3-point bending concentrates the maximum bending moments in the specimen's middle. Introducing combined mode 1 and mode 2 stresses, making objective determination of tensile strength more challenging. The undulating surface patterns typical in 3D printed specimens can cause stress concentration and premature failure unless meticulously removed by saw cutting or grinding without introducing new imperfections. There's a 4-point bending test where limited specimen alteration is considered a more practical method to determine IBS compared to direct tensile tests. Given the 3D printed structure face diverse loading scenarios, the use of 4-point bending for characterization is warranted, while direct tensile test remains essential for accurate parameter characterization. The European norm 196-1 standard requiring specimen of 160 in the length and then 40 in the cross section is widely used for 4-point bending tests in literature. In-depth computational analysis requires conducting shear tests under confining normal stress conditions and without it. To define the model parameters of interlayer regions, such as shearing adhesion, fracture energy, and the friction and dilatancy angles. At a minimum, determining the shearing adhesion is crucial for structure design. Assessing whether there is adequate shear resistance along the interlayer regions to withstand diverse loads, predominantly involving shear and flexure. There is a wealth of characterization tests and findings from layered construction materials like masonry and timber, adoptable for 3D printed concrete. Several shear tests have been proposed, each with varying success in achieving a uniform shear stress state. Among these, the IOC pass-through test reportedly produces the most uniform shear stress distribution if notice of appropriate geometry or meticulously saw cut. Existing shear test results on 3D printed concrete elements utilizes specimen sized at 80 by 30 by 160 millimeters, which are the height, thickness, the length, with specific roller spacing at notches. Utilizing linear elastic finite elements analysis, the shear stress distribution along the interlayer region can be computed, providing an average shear adhesion strength with reasonable accuracy. Characterizing shear fracture energy demands accurate measurement of shear slip, displacement along the interface, which includes dilatancy and deformation away from the shearing interface. Employing additional LVDTs across the shearing interface enhances accuracy while compensating for dilatant deformation recorded by the diagonal LVDT. For characterizing the friction coefficient, conducting more shear tests under steady and uniform compressive normal stress conditions is necessary across at least the two non-zero compressive stress levels. This setup, essential in masonry testing, accurately defines the shear strength at zero confining stress, fracture energy, and both frictions and dilatancy coefficient. Despite less uniform shear stress distribution in the shearing interface, triplet tests developed for masonry can be adapted for 3D printed concrete material. Presently, destructive testing methods like compression crushing, direct tensile test, flexure, shear, splitting tests are employed to measure the lack of fusion between filament layers in 3D printed concrete. While techniques such as scanning electron microscopy, which is a SEM, and X-ray computed tomography are used to visually inspect the interfacial regions between the filaments, they lack the ability to quantitatively measure the extent of lack of fusion. Moreover, these methods involve extracting small specimens from larger ones, making them indirect destructive tests. Although destructive tests are preferred for capturing actual interlayer bond strength, they might not always be practical for larger 3D printed concrete projects. To address this limitation, non-destructive testing techniques can be considered. Odaira and Matsuzawa demonstrated success in estimating the strength of cold joints in concrete using ultrasonic attenuation. Given the similarity of interface region to cold joints, this approach could be adapted for assessing 3D printed concrete structure. Another study by Ulfs et al. From the Eindhoven University applied ultrasonic wave transmission (UWT) to 3D printable concrete and suggested its suitability as a non-destructive method for characterizing early age properties like compressive strength and Young's modulus. Similarly, a researcher, Professor Ma, utilized piezoelectronic zirconate titanate PZT patches to monitor real-time changes in mechanical properties during both fresh and hardened states of 3D printed concrete material. Their findings supported the use of smart PZT patches for effective damage detection and quantification. Employing NDT methods seems highly promising for quantifying a lack of fusion between layers. Sure, we'll conclude this work session here. We've covered interlayer bond strength, lack of fusion, and the influencing factors, and the assessment techniques. Next week, we'll explore software tools tailored for 3D concrete printing and will be used during the printing process. Hang in there, and I'll see you very soon.